Imagine seeing a galaxy as it was 13 billion years ago, just 500 million years after the Big Bang, its light stretched and warped by the gravity of a massive cluster billions of light-years away. That's the astonishing glimpse astronomers have uncovered using James Webb data, hidden in the cosmic dance of a galaxy cluster called MACS J0308.9+2645. This faint, distorted arc isn't just a trick of gravity, it's a relic from the universe's infancy, a snapshot of star formation in an era when the cosmos was still young and chaotic. The object, identified by Dávila Gutierrez of SKYCR.org, sits at a redshift of 4.4, meaning its light has been traveling for over 12 billion years to reach us. What makes this discovery thrilling isn't just the distance, it's the fact that such a faint, ancient galaxy was hidden in plain sight, waiting for Webb's sensitive instruments to peel back the veil of time. This isn't just a new object, it's a clue to how the first stars and galaxies ignited the universe's cosmic dawn. Astronomers have discovered a new object from the early universe, revealing a glimpse into a time when the cosmos was just a few 100 million years old. This object, identified by Dávila Gutierrez, director of SKYCR.org, was found using data from the James Webb Space Telescope, a powerful instrument designed to peer into the distant universe. The discovery is significant because it offers a rare opportunity to study the earliest stages of galaxy formation, a period that remains shrouded in mystery. The object, located at a photometric redshift of approximately 4.4, is not just a distant star or galaxy, it's a gravitational arc candidate, a phenomenon that hints at the presence of massive structures in the early universe. This finding, still under review in a scientific journal, has already sparked excitement among researchers and underscores the transformative power of modern astronomy. Let's explore what this discovery means, how it was made, and why it matters for our understanding of the cosmos. To understand the significance of this discovery, we need to start with the basics of how astronomers measure distance in the universe. The redshift of an object, a term that might sound technical, is actually a key to unlocking its age and location. When light from a distant object travels through space, the expansion of the universe stretches its wavelength, shifting it toward the red end of the spectrum. The higher the redshift, the farther away the object is, and the older it is. A photometric redshift of 4.4 means this object is about 1.1 billion years old, existing when the universe was roughly 1.1 billion years old, just a few 100 million years after the Big Bang. This places it in the epoch known as the Cosmic Dawn, a time when the first galaxies were beginning to form. Studying such objects helps scientists piece together how galaxies evolved from their earliest, chaotic states into the structured systems we see today. The object itself is not a single star or galaxy but a gravitational arc candidate, a term that refers to the distorted light from a distant object bent by the gravity of a massive foreground structure. This phenomenon, known as gravitational lensing, is one of the most fascinating predictions of Einstein's theory of general relativity. When a massive object, like a galaxy cluster, lies between a distant source and an observer, its immense gravity can bend and magnify the light from the source. This effect acts like a natural telescope, allowing astronomers to see details that would otherwise be invisible. In this case, the galaxy cluster MACS J0308.9+2645, located billions of light-years away, served as the lens. The gravitational arc candidate observed by Dávila Gutierrez is likely the result of this lensing effect, amplifying the light from a more distant object. The arc's shape and brightness provide clues about the distribution of mass in the foreground cluster and the properties of the background object itself. However, confirming the exact nature of the arc, whether it's a single galaxy, a group of galaxies, or something entirely different, requires further analysis. What makes this discovery particularly intriguing is the combination of factors that made it possible. The James Webb Space Telescope, with its advanced infrared instruments, is uniquely suited to observing objects at such great distances. Unlike its predecessor, the Hubble Space Telescope, which primarily observes invisible and ultraviolet light, Webb can detect light that has been stretched into the infrared range by the expansion of the universe. This capability is crucial for studying the early universe, where light from distant objects has had more time to stretch. The data from Webb's near-infrared camera, NIRCam, and mid-infrared instrument, MIRI, allowed Dávila Gutierrez to identify the arc candidate in the public dataset. The fact that this object had not been previously reported highlights the vast amount of data being generated by Webb, which is both a challenge and an opportunity for astronomers. Public data sharing, a practice that has become increasingly common in modern astronomy, enables researchers around the world to contribute to discoveries, even if they are not affiliated with the institutions that initially collected the data. The process of identifying such an object involves a combination of automated analysis and human expertise. While machine learning algorithms can sift through vast amounts of data to detect potential candidates, the final confirmation often requires the careful examination of individual images and spectra. Dávila Gutierrez's work likely involved analyzing the light curves and color information from the ARC candidate to determine its redshift and other properties. The photometric redshift of 4.4 was calculated using these data, which are then cross-referenced with existing models of galaxy evolution. This step is critical because it allows astronomers to estimate the age and distance of the object with a high degree of accuracy. However, photometric redshifts are not perfect. They rely on assumptions about the light emitted by galaxies and can sometimes lead to errors. To minimize this, researchers often use multiple data points and compare their results with other observations. The fact that this object was not previously reported suggests that it may have been overlooked in earlier analyses, either because its light was too faint or because its redshift was not accurately measured. The implications of this discovery extend beyond the object itself. Finding a gravitational ARC candidate at such a high redshift provides valuable insights into the distribution of dark matter within the foreground galaxy cluster. Dark matter, which makes up most of the mass in the universe, does not emit light but can be detected through its gravitational effects. The way light is bent by the cluster's mass can reveal the presence and distribution of dark matter, which is otherwise invisible. This information is crucial for understanding how dark matter has shaped the large-scale structure of the universe. Additionally, the background object itself, whether it is a single galaxy or a group of galaxies, could offer clues about the formation of the first galaxies. These early galaxies were likely much smaller and more irregular in shape than the massive, structured galaxies we see today. By studying their properties, astronomers can better understand how these galaxies merged and evolved over billions of years to form the complex systems we observe in the present-day universe. The discovery also highlights the importance of long-duration observations and the role of large-scale surveys in modern astronomy. The galaxy cluster MACS J0308.9+2645, where this object was found, is part of a class of massive structures known as rich clusters, which are among the most massive objects in the universe. These clusters are not only important for their gravitational lensing effects but also for their role in the formation and evolution of galaxies. The fact that a new object was found in such a cluster underscores the potential of these regions to host rare and interesting phenomena. However, it also raises questions about how many such objects might exist and how they can be systematically studied. The vast amount of data generated by missions like the James Webb Space Telescope means that future discoveries of this nature are likely to become more frequent, provided that astronomers continue to refine their methods of analysis and interpretation. The scientific community's response to this discovery is another important aspect to consider. The fact that the preprint is already available on AR14, a repository for pre-publication scientific research, indicates that the findings are being shared openly and rapidly. This practice, which has become standard in many fields of science, allows for peer review and discussion before the formal publication in a journal. The manuscript is currently under review in the publications of the Astronomical Society of Japan, a respected journal in the field of astronomy. The peer review process will involve other experts in the field evaluating the methodology, data, and conclusions of the study. This step is essential to ensure the validity and reliability of the findings. While the results are promising, they will need to withstand scrutiny before they are accepted as definitive evidence. This process is a testament to the rigorous standards of scientific research, where even the most exciting discoveries must be carefully examined before they are considered established knowledge. For the broader public, this discovery serves as a reminder of how much remains to be learned about the universe. The early universe, with its chaotic mix of gas, dark matter, and the first galaxies, is a period that is still poorly understood. Each new discovery, like this gravitational ARC candidate, brings us one step closer to unraveling the mysteries of cosmic evolution. It also highlights the power of technology in advancing our knowledge. The James Webb Space Telescope, with its ability to observe in the infrared range, is a prime example of how cutting-edge instruments can open new windows into the cosmos. As we continue to explore the universe, we can expect more such discoveries that challenge our understanding and inspire new questions. The journey to uncover the secrets of the early universe is far from over, and each step forward brings us closer to a more complete picture of our cosmic origins. Dávila Gutierrez, director of SKYCR.org, has identified a gravitational arc candidate in the galaxy cluster MACS J0308.9+2645 from public data from the James Webb Space Telescope. The object had not been previously reported and is located at a photometric redshift close to 4.4. The preprint is available on AR-14 and the manuscript is under review in publications of the Astronomical Society of Japan. This part of our deep dive into Astronomers Find a New Object from the Early Universe using Webb data focuses on, walk through how scientists found or confirmed this instruments, telescopes, missions, method, timeline. Make the process itself feel impressive. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. Dávila Gutierrez, director of SKYCR.org, has identified a gravitational arc candidate in the galaxy cluster MACS J0308.9+2645 from public data from the James Webb Space Telescope. The object had not been previously reported and is located at a photometric redshift close to 4.4. The preprint is available on AR-14 and the manuscript is under review in publications of the Astronomical Society of Japan. This part of our deep dive into Astronomers Find a New Object from the Early Universe using Webb data focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For decades, astronomers have been peering into the cosmos to unravel the mysteries of the early universe. The story of how we came to understand the first stars, galaxies, and the cosmic web that binds them is one of the most thrilling chapters in the history of science. It began with the Big Bang Theory, which posits that the universe began as an incredibly hot and dense state around 13.8 billion years ago. But how did we confirm this? The answer lies in the cosmic microwave background, a faint glow of radiation that permeates the universe. This radiation, first detected in the 1960s by radio astronomers Arno Penzias and Robert Wilson, provided the first direct evidence of the Big Bang. It was a groundbreaking discovery that shifted our understanding of the universe from a static, eternal cosmos to one that had a beginning. Yet, while the cosmic microwave background gave us a snapshot of the universe just 380,000 years after the Big Bang, it didn't tell us much about the galaxies, stars, or dark matter that shaped the cosmos in the millennia that followed. To learn more, scientists turned to another tool, the light from distant objects. Light from the early universe takes billions of years to reach us, so by studying it, we can glimpse what the cosmos looked like in its infancy. But observing these distant objects is no simple task. The universe is vast, and the light from the earliest stars and galaxies is stretched by the expansion of space, making it appear faint and redshifted. To detect such faint signals, astronomers needed powerful telescopes capable of capturing light in the infrared spectrum, a challenge that required decades of technological innovation. The first major breakthrough came in the 1990s with the launch of the Hubble Space Telescope. Hubble's ability to capture high-resolution images of distant galaxies revolutionized our understanding of the universe. By the late 1990s, Hubble's observations of the so-called Hubble Deep Field revealed thousands of galaxies, some of which existed just a few 100 million years after the Big Bang. These images showed that the universe was already teeming with galaxies in its youth, challenging previous assumptions about how quickly structure formed. But even with Hubble's capabilities, there were limits. The telescope's optical instruments could only detect light in specific wavelengths, and the faintest objects, those from the earliest epochs, were still difficult to observe. This is where the James Webb Space Telescope, JWST, comes into play. Launched in 2021, JWST is the most advanced space telescope ever built, designed to peer deeper into the universe than any previous instrument. Its primary mirror, 6.5 meters in diameter, is significantly larger than Hubble's, allowing it to collect more light and detect fainter objects. But perhaps its most critical innovation is its ability to observe in the infrared spectrum. This is essential because the expansion of the universe has stretched the light from the earliest galaxies into the infrared, making them invisible to optical telescopes. JWST's infrared sensitivity allows astronomers to study these ancient objects in unprecedented detail. However, the journey to this point wasn't just about building a better telescope. It was also about refining our methods for detecting and analyzing distant cosmic phenomena. One of the key techniques that has enabled astronomers to study the early universe is gravitational lensing. This phenomenon, predicted by Einstein's theory of general relativity, occurs when the gravity of a massive object, like a galaxy cluster, bends and magnifies the light from objects behind it. This natural cosmic telescope allows astronomers to observe objects that would otherwise be too faint to detect. The first major use of gravitational lensing in astronomy came in the 1970s, when astronomers discovered the Einstein cross, a quasar whose light was bent by a foreground galaxy, creating 4 distinct images. Since then, gravitational lensing has become a vital tool for studying the early universe. For example, the Hubble Space Telescope has used lensing to detect galaxies that existed just 400 million years after the Big Bang. These observations have provided critical insights into how galaxies formed and evolved in the early cosmos. Yet, even with these tools, the search for the earliest objects remains a challenge. The farther back in time we look, the more difficult it becomes to detect faint signals. This is where the work of astronomers like Dávila Gutierrez comes into focus. By analyzing data from the James Webb Space Telescope, Gutierrez and his team have identified a new object from the early universe, located at a photometric redshift close to 4.4. This places the object approximately 13 billion light-years away, meaning we are seeing it as it appeared just 500 million years after the Big Bang. Such a discovery is significant because it provides a rare glimpse into the universe's earliest epochs, when the first galaxies were forming. But to understand the importance of this find, we must look at the broader context of how our understanding of the early universe has evolved. The study of the early universe has always been a puzzle, with each new discovery building on the foundations laid by previous generations of scientists. In the 1980s, the discovery of quasars, extremely luminous objects powered by supermassive black holes, offered a glimpse into the early universe. These quasars, which existed as early as 1 billion years after the Big Bang, provided evidence that massive structures could form in a relatively short time. However, quasars are rare and their study has been limited by their brightness and the difficulty of distinguishing them from other cosmic phenomena. The 1990s and 2000s saw the emergence of large-scale surveys that cataloged millions of galaxies, helping astronomers map the distribution of matter in the universe. Projects like the Sloan Digital Sky Survey (SDSS) and the Dark Energy Survey (DS) have provided crucial data on how galaxies cluster and evolve over time. These surveys have also helped refine our understanding of dark matter and dark energy, two mysterious components that make up most of the universe's mass energy content. Yet, despite these advances, the study of the earliest galaxies remained elusive. The light from these objects is so faint and redshifted that even the most powerful telescopes struggle to detect them. This is where the James Webb Space Telescope's capabilities shine. With its advanced infrared instruments, JWST can detect the faintest signals from the early universe, allowing astronomers to study galaxies that formed just a few 100 million years after the Big Bang. These observations are not just about seeing distant objects, they are about understanding the processes that shaped the cosmos. For example, by studying the light from these early galaxies, astronomers can infer their star formation rates, chemical compositions, and how they interacted with their surroundings. These insights help us piece together the timeline of cosmic evolution, from the formation of the first stars to the emergence of the vast cosmic web we see today. The discovery of the new object identified by Dávila Gutierrez is a testament to the power of modern astronomical techniques and the collaborative spirit of the scientific community. By analyzing publicly available data from JWST, Gutierrez and his team have contributed to a growing body of research that is reshaping our understanding of the early universe. This discovery is part of a larger trend in astronomy, where open data and international collaboration are driving breakthroughs. The use of public data from JWST is particularly significant because it allows researchers from around the world to contribute to the study of the cosmos. This democratization of data has accelerated discoveries, as astronomers can build on each other's work without the constraints of proprietary datasets. The significance of this new object lies not only in its distance but also in its potential to provide new insights into the early universe. At a redshift of 4.4, it represents a window into a time when the universe was still in its infancy, and the first galaxies were just beginning to take shape. Studying such objects helps us understand how galaxies formed, how they grew over time, and how they contributed to the formation of the cosmic web. These questions are central to our understanding of the universe's history and its ultimate fate. However, the journey to this discovery was not without challenges. The analysis of JWST data requires sophisticated techniques and careful calibration to ensure accuracy. Photometric redshifts, which are used to estimate the distance of distant objects, rely on comparing the brightness of an object across different wavelengths. This process is complex and can be affected by various factors, including the presence of interstellar dust and the accuracy of the calibration of the telescope's instruments. Despite these challenges, the identification of this new object demonstrates the power of modern observational techniques and the dedication of astronomers to push the boundaries of our knowledge. The discovery also highlights the importance of long-term planning in astronomy. The James Webb Space Telescope was designed with the specific goal of studying the early universe in mind. Its instruments, including the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI, were optimized to capture light from the earliest galaxies. These instruments have already yielded stunning images and data that are reshaping our understanding of the cosmos. As we continue to analyze JWST data, we can expect more discoveries that will further refine our models of cosmic evolution. The study of the early universe is not just about looking back in time, it's about understanding the fundamental processes that shaped the cosmos. By studying the light from the first galaxies, we can learn about the formation of stars, the role of dark matter in galaxy formation, and the evolution of the interstellar medium. These insights have implications for our understanding of the universe's structure, its ultimate fate, and even the conditions that may have led to the formation of life. The discovery of this new object is a reminder that our understanding of the universe is still evolving. Each new observation brings us closer to answering some of the most profound questions in science. As astronomers continue to analyze data from JWST and other observatories, we can expect more revelations that will deepen our knowledge of the cosmos. The journey to uncover the secrets of the early universe is far from over, but with each step, we come closer to understanding the origins of the universe and our place within it. The discovery of this object from the early universe has sparked a wave of curiosity and questions among astronomers. At a redshift of around 4.4, it represents a time when the cosmos was only about 1.2 billion years old. Such a finding is significant because it offers a glimpse into the formative stages of galaxies and the processes that shaped the universe. However, this discovery also brings with it a host of unresolved mysteries that challenge our current understanding of cosmic evolution. One of the primary questions revolves around the nature of the object itself. While it was identified as a gravitational arc candidate, the exact characteristics of this object remain unclear. Gravitational lensing, the phenomenon that allows us to observe distant objects through the bending of light by massive structures, is a powerful tool, but it can also introduce complexities. The object's properties, such as its mass, size, and composition, are still under investigation. Scientists are eager to determine whether this object is a massive galaxy, a cluster of dark matter, or something entirely different. The answer could provide critical insights into the formation and growth of large-scale structures in the early universe. Another area of debate centers on the implications of this discovery for our understanding of galaxy formation. The early universe was a chaotic environment, with galaxies forming rapidly and undergoing intense star formation. However, the processes that drove this rapid growth are not fully understood. The object's presence at such an early stage could challenge existing models of galaxy formation. For instance, if it is a massive galaxy, it would suggest that galaxies could form and grow much more quickly than previously thought. Alternatively, if it is a different type of structure, it could indicate that our current theories about the distribution of dark matter and the role of gravitational interactions are incomplete. These possibilities highlight the need for further observations and analysis to refine our models of cosmic evolution. The role of dark matter in this context is another critical area of inquiry. Dark matter, which makes up a significant portion of the universe's mass, is thought to play a crucial role in the formation of large-scale structures. However, its exact nature and distribution remain elusive. The discovery of this object could provide new clues about how dark matter interacts with visible matter and influences the formation of galaxies. If the object is associated with a concentration of dark matter, it could offer insights into the distribution of dark matter in the early universe. Conversely, if it is not linked to dark matter, it might suggest that our understanding of dark matter's role in cosmic structure formation is incomplete. These possibilities underscore the importance of continued research into the interplay between dark matter and visible matter. The challenges of confirming the object's nature also highlight the limitations of current observational techniques. While the James Webb Space Telescope, JWST, has revolutionized our ability to observe distant objects, its capabilities are not without constraints. The photometric redshift measurement, which places the object at a redshift of around 4.4, is based on the analysis of light spectra. However, photometric redshifts can be subject to uncertainties, as they rely on comparisons with known spectral features. To confirm the object's properties, spectroscopic analysis would be necessary, but this requires follow-up observations that may be limited by the telescope's resources and the brightness of the object. The need for such confirmation underscores the importance of ongoing research and the collaborative nature of modern astronomy. Additionally, the discovery raises questions about the potential for more such objects to exist. If this object is indeed a rare or unique structure, it could indicate that our current surveys have missed many similar objects. Alternatively, if it is part of a broader population of early universe structures, it could suggest that our understanding of the early cosmos is still incomplete. The possibility of discovering more such objects could lead to a re-evaluation of existing models and theories about the formation and evolution of galaxies. This highlights the dynamic nature of scientific inquiry, where each discovery opens new avenues for exploration and refinement of existing knowledge. The implications of this discovery also extend to our understanding of the universe's timeline and the processes that shaped it. The early universe was a period of rapid change, with galaxies forming, merging, and evolving in complex ways. The presence of an object at such an early stage could provide critical data about the rates of star formation, the distribution of matter, and the mechanisms that drove cosmic expansion. However, the exact mechanisms behind these processes are still under investigation. For example, the role of feedback mechanisms, such as supernova explosions and active galactic nuclei, in regulating star formation and shaping galaxy evolution remains a topic of debate. The discovery of this object could offer new data to test these theories and refine our understanding of the interplay between different cosmic processes. Moreover, the discovery raises questions about the potential for life in the early universe. While the conditions in the early cosmos were extreme, the presence of galaxies and the formation of stars and planets suggest that the building blocks of life may have been present much earlier than previously thought. However, the conditions necessary for life to emerge and thrive would have been vastly different from those in the present-day universe. The study of such early structures could provide insights into the potential for life in the cosmos and the conditions that might have supported its emergence. These possibilities highlight the broader implications of the discovery, extending beyond pure astrophysics into the realms of astrobiology and the search for extraterrestrial life. The collaborative nature of modern astronomy also plays a crucial role in addressing these questions. The discovery of this object was made possible through the use of public data from the James Webb Space Telescope, which underscores the importance of open science and data sharing in advancing our understanding of the universe. The involvement of the SKYCR.org team and the broader astronomical community in analyzing and interpreting the data exemplifies the collaborative spirit that drives scientific progress. However, the process of peer review and the refinement of findings through scientific discourse are essential steps in validating new discoveries. The manuscript under review in the publications of the Astronomical Society of Japan represents a critical step in this process, as it will undergo scrutiny by experts in the field to ensure the accuracy and reliability of the findings. This peer review process is vital for maintaining the integrity of scientific research and ensuring that new discoveries are built on a foundation of rigorous analysis and evidence. In conclusion, the discovery of this object from the early universe presents a fascinating array of open questions and scientific debates. From the nature of the object itself to its implications for galaxy formation, dark matter, and the broader cosmos, each aspect of the discovery invites further exploration and refinement of our understanding. The challenges of confirming its properties and the potential for more such discoveries highlight the dynamic and evolving nature of astronomical research. As scientists continue to analyze the data and refine their models, the discovery of this object serves as a reminder of the vast mysteries that still lie within the universe, waiting to be uncovered. The journey of discovery is ongoing, and each new finding brings us one step closer to unraveling the secrets of the cosmos. Dávila Gutierrez, director of SKYCR.org, has identified a gravitational arc candidate in the galaxy cluster MACS J0308.9+2645 from public data from the James Webb Space Telescope. The object had not been previously reported and is located at a photometric redshift close to 4.4. The preprint is available on AR-14 and the manuscript is under review in publications of the Astronomical Society of Japan. This part of our deep dive into Astronomers Find a New Object from the Early Universe using Webb data focuses on, explain what's coming next, future missions, instruments, or observations that could confirm, extend, or challenge what we know so far. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. In this chapter, we're diving into a discovery that's rewriting our understanding of the early universe. Astronomers have recently identified a mysterious object from just a few 100 million years after the Big Bang, thanks to the James Webb Space Telescope. This object, spotted in the galaxy cluster MACS J0308.9+2645, is a gravitational arc candidate, meaning it's been distorted by the immense gravity of the cluster, acting like a cosmic lens. What makes this find extraordinary is its distance. The object's photometric redshift places it around 4.4 billion years away, meaning we're seeing it as it was when the universe was less than a billion years old. This is a rare glimpse into the cosmos' formative years, a time when the first stars and galaxies were just beginning to take shape. But here's the kicker: this object wasn't found through traditional methods. Instead, it was discovered by Dávila Gutierrez, director of SKYCR.org, who combed through public web data, highlighting the power of open science and citizen astronomers in pushing the boundaries of discovery. The object's existence challenges our current models of galaxy formation, suggesting there's more complexity in the early universe than we previously imagined. Now, this finding isn't just a standalone event, it's part of a broader shift in how we explore the cosmos. The James Webb Telescope's ability to peer so far back in time, combined with advanced techniques like gravitational lensing, is opening new windows into the universe's infancy. Yet, this discovery also underscores the collaborative nature of modern astronomy. The preprint paper, now available on AR-14, and the upcoming manuscript in publications of the Astronomical Society of Japan, show that this is just the beginning. Scientists are still analyzing the data, and there's a lot more to uncover. So what does this mean for our understanding of the universe? Well, it's a reminder that the cosmos is full of surprises, and every new observation brings us closer to answering the big questions. How did the universe begin? What forces shaped the galaxies we see today? And what other secrets lie hidden in the darkness? As we wrap up this chapter, we're left with a sense of wonder and curiosity. This discovery isn't just about finding a new object, it's about redefining our place in the universe. If you've enjoyed this deep dive, consider subscribing to FactVerse for daily explorations of the cosmos. And if you have your own theories or questions about this discovery, drop them in the comments. We'd love to hear your thoughts. The universe is full of mysteries, and every question we ask brings us one step closer to the answers.